Hello Year 11, it's Miss Bailey here. So for your Do Now today, I'd like you to be considering what this symbol at the top means. So this, where we've got an arrow or a half arrow going in one direction and a half arrow going in the other direction. So what does this symbol mean? And I've given you a hint at the bottom. So pause the video whilst you have a think about these. Okay, so what we're going to be looking at today is reversible reactions, and we're going to talk about 3 reversible reactions together now. So litmus paper, which you will have come across when you looked at acids and alkalis, this is used to test for the acidity or alkalinity of a substance. So by dipping in the litmus paper, we can use that indicator to tell us whether something is acidic or alkali because it changes colour. Now this is actually a reversible reaction because what we can do is we can put our blue litmus into an acid and it will turn red, but we could then take that red litmus and put it into an alkali and that reverses the reaction, making it turn blue like it was to start with. Another example of reversible reaction is the decomposition of ammonium chloride. So decomposition is where we break down the compound into multiple substances. So in this case, we break ammonium chloride down into ammonia and hydrogen chloride. Now, this type of decomposition is a thermal decomposition. Because we're using a Bunsen burner, we require that thermal energy in order to break that substance down. But what you'll notice is that this is a reversible reaction because once we have broken the compound into these components, they can actually then reform when they're not experiencing that thermal energy that they had to start with. And so we get a reversible reaction set up between the ammonium chloride and its decomposition products. Another example is looking at copper sulfate. So you would have made these blue copper sulfate crystals last year, again during that salts topic. So what we have here is a reversible reaction looking at heat and water. So you'll notice with this hydrated, so hydrated means that we have water available, we have this 5H2O. So what that tells us is that for every formula unit of copper sulfate, we have 5 water molecules that are also trapped. And in this form of copper sulfate, they appear as blue crystals. But with our anhydrous, so anhydrous like an for anti, we have no water, and you can see that in the chemical formula as well. We don't have that 0.5H2O. And this is a white powder. So if we heat those blue crystals, we end up removing the water from the copper sulfate. And so we get the white powder plus the water, which will then be evaporated into the surroundings. But we can reverse this reaction by simply adding water. And so here we have a reversible reaction set up, looking at whether we apply heat or whether we apply water as to which side the reaction is going to go. So these are 3 examples of reversible reactions. What I'd like you to have a think about now is what a reaction profile might look like. So thinking about going from our reactants to our products. What's it going to look like for our forwards reaction, and what's it going to look like for our backwards reaction? So pause the video whilst you have a think. Okay, so for this I've drawn my products lower than my reactants, so we're going to assume that it's an exothermic reaction, as we're going to have a negative delta H. A negative energy change, so our energy is released to the surroundings, which would cause an increase in our temperature. So in this example, we've gone from reactants to products, and to do that we've had to apply energy to overcome our activation energy, that minimum energy needed for the reaction to happen. So if we're going over the hill in this direction for our forwards reaction, when we go from our products back to our reactants for the backwards reaction, we're actually just going back over the same hill. So we can be considering that our reaction profile is just going to look like a mirror image, having a different activation energy going in the other direction. However, the energy change is going to be equal but opposite, because we're now moving from the products to the reactants. So in one direction it will be endothermic, but in the other it will be exothermic. So here we looked at going from our reactants to our products being exothermic, but then when we go from our products to our reactants, it is now an endothermic reaction because we take in that energy. So for the remaining part of this lesson, if you can go onto the Oak Academy link that's attached in the PowerPoint, and if you can complete their worksheet which is attached there. So they will go into a lot more detail about these reversible reactions, and you'll have the opportunity to do some practice with what you have learned. Thank you all for watching, and see you next time.